Ferguson, who is VP of Marketing and Strategic Alliances at Lynx Technologies. Prior to joining Lynx in 2019, Ian spent over 10 years at Arm, where his positions included VP of Ecosystem Development at the IoT Services Group, VP of Worldwide Marketing and Strategic Alliances, and VP of Segment Marketing. More recently, Ian has been consulting for a range of clients focused on technologies such as blockchain, machine learning, and robotics. Gartner has started to postulate that in a few years' time, laws could be made and enforced whereby CEOs are held responsible for the misoperation of IoT systems that a specific company produces. The challenges here is that industrial Internet of Things systems are extremely complex. They consist of multiple subsystems, often delivered by a myriad of companies, often at different times. In short, cybersecurity is a team sport, meaning the average time to identify a breach and respond with a patch can be lengthy. However, Ian's presentation today will look at the significant strides that this industry is making and will offer some predictions around how the next set of challenges around human-robot collaboration, artificial intelligence, and suboptimal hardware can be addressed. So, without further ado, I will hand over to Ian.
Thank you, Joe, and thanks everyone spending some of your precious time with me. Quite a formal introduction, and I'll try to live up to the billing. Just quickly, a little bit about the company where I'm currently working, Lynx. We've been around for about 30 years, about 20 years in working on software for mission critical systems. So these are the systems that just have to work all the time. That started with real-time operating systems. It moved to hypervisors, and now it's sort of software frameworks that help people connect up our technology, third-party technology, and their own bare metal code. And that sort of started in the aerospace industry, and now, as you know, more systems are becoming autonomous and moving around, and as Joe said in the interaction, people are starting to work alongside robots in factory environments, for example. We see the requirements of what's had to keep us safe in the sky at 30,000 feet, coming down to the shop floors, to our streets, and a number of other applications. And as Joe said with the introduction, what triggered me on these thoughts was this piece from Gartner a couple of months ago, in the middle of in 2020, and frankly, the article that you sort of see here was a little bit of clickbait. You click there, and there wasn't a lot of data, but it was an interesting postulation that CEOs could face jail time, for IoT attacks, and it's an interesting topic, and I sort of went back to the times in the early 2000s with Sarbanes-Oxley, where CFOs could be felt accountable if their books were not kept in order. And I just started to think of that analogy into our secure IoT world, and what's going to happen if that sort of Sarbanes-Oxley and the impact on the CFOs, how that translates to an IoT security area and holding CEOs accountable. And so then I thought about a great article just came out in March 2017 from Microsoft. And this outlined what they called 7 properties of highly secure devices. And so it's a great piece. It's online. Be able to get you the link. It's pretty easy just to search actually with that title. But my point here is this was 3.5 years ago, and if you look at the functions that are being outlined, a hardware root of trust, minimizing the footprint and the attack surface of your trusted code. Compartmentalization of your software components, so that if somebody breaks in, they don't get access to the full contents of the cookie jar. They get access to a subsection of that. And the Microsoft analogy 3.5 years ago was that when you leave your house today, you lock your front door with a connected IoT device. The analogy there is that before you leave the house, you don't just lock your front door, but you lock your bedroom door, your living room door, your bathroom door, your kitchen door, so that if somebody does break in, they get access into only that room. And so nothing on here is brand new. And I think the frustration has been, why is this taking so long? There are chips starting to come out with some of these capabilities. You see industry players like ARM announce their platform security architecture in about the same time frame, actually, as Microsoft released this paper in early 2017. And yet, you can't go through a week in business right now without reading about some sort of hack that's compromised either people's personal data or actually taken over a device to get it to do malicious things. So why are things taking so long? And I think there's a couple of aspects to it. On one side, this technology is not free to put down onto chips. Encryption blocks, hardware encryption blocks are probably larger than today's CPUs. You're adding extra memory to secure your assets. It boosts, it extends the size of your chip, and that means cost. So these chips are more expensive than if you have no security provisioning on them at all. And so what has to happen is there has to be demand coming from places of influence that actually say, hey, if you build these types of capabilities into your components, we will buy them. In fact, we will only buy that type of technology to create the pull from the market. And what I'm hopeful now of is a couple of things that actually shows that will happen. Despite my English accent, I'm based in the US. But in the US, just last month, the House of Representatives passed a crypto security bill, 1668, where they said that they would, for the US government and its agencies, for critical infrastructure, they would mandate a set of functions that had to be in those products in order for them to buy it, related to security. And it was a pretty good starting point, and it had a similar list of things to some of the elements that Microsoft had outlined. It's missing a couple of things, and I'll talk a little bit about my thoughts on the future later, but it was a good start. What you're seeing here is sort of a UK equivalent, and there was a European piece of legislation passed a few years ago, and that then has rolled out into the different countries across Europe, and that is basically saying for critical infrastructure, and that will be transportation, healthcare, energy. Again, a report online. There is a set of capabilities that we need to have in these IoT devices that are going to be connected into these, systems that just have to work all the time. And I think from a top level demand point of view, that's great, right? There's a end place that will actually say that these are the sorts of systems that we will need to have in our hospitals, in our distribution of electricity, those kinds of applications. Fantastic. The other thing is that the European courts, and every country is going to do it slightly differently, they will be empowered to actually put punitive fines on people that are actually not able to prove that their systems are aligned with these sorts of functions, or able to support, have latest and greatest patches. And so I think, one of the things to watch for is, how does that get policed? And I actually think, as Joe said in the introduction, you've got with these IoT systems a number of pieces that are having to be connected together. It doesn't all come from one vendor. It's not as simple as you just buy your smartphone from Apple or Samsung. If you're in a manufacturing plant, you're going to be assembling a lot of pieces together. With crypto security, you're only as strong as your weakest link, right? So, think back to your favorite hack story where casinos in Reno, Nevada have been accessed via a connected goldfish tank, and people's assets and banking information and casino gambling histories can get access through a goldfish tank. So people are going to have to look at the entire infrastructure of a hospital in Letchworth, or manage the electricity of Manchester, and are going to need to understand that all of these different pieces are up to a certain level of security. If there's a known patch, you have to be able to see that those patches have been applied. And I think instead of paperwork, that is going to have to be digital. And so I think you'll see people evolving to architectures using probably some sort of form of blockchain technology, where systems interact with central infrastructure that can prove that a particular subsystem has been updated to the latest and greatest patches to have addressed known bugs X, Y, and Z. So I think we'll see that coming forward. I think COVID and a number of other things in the UK have sort of slowed people's focus on implementing and mandating these sorts of plans. But I think we will see a stronger push, both here where I'm based in the US and across Europe, on actually making sure that these systems are have the right levels of security, the hardware roots of trust and compartmentalization, those pieces I described earlier, and will actually start to look at how they implement and not just threaten, but start to carry out punitive measures if they're found to be lacking from a technology point of view. So that's great on the hardware side. I think, again, like Joe said, security is going to be a team sport, not just hardware, software, but all the way up the value chain and back down. And I think one of the reasons, I don't think we're going to get to a place anytime soon where CEOs are going to go to jail for IoT hacks. But my take on that Gartner article earlier is going to be that, CEOs are going to be driving very strongly to make sure systems are connected, because if a system is hacked, it's going to be their face and their company that's on the front of Forbes magazine or BBC technology areas as being the company that got hacked. And I think one of the so whats and why you see more companies like OEMs taking control of their hardware requirements is that they're actually wanting to feel far more comfortable about the systems that they're putting out, rather than just relying on black box hardware coming in from other places. So, Tesla designing their own chips, a number of other automotive companies not maybe going as far as designing their chips, but actually specifying what those systems have to look like. Part of it is about managing their supply chain, but part of it is about raising the bar on security. From a software point of view, what we're seeing is people put more and more functionality onto these multi-core platforms. And so you can have done some great things in the hardware, but you also have to think about, from a software point of view, of spreading out and compartmentalizing your software pieces so that systems aren't sharing memory. If a particular area of a system fails, the whole system doesn't come down. You again have to sort of compartmentalize it. And multi-core processors are great, but they cause some massive problems in terms of real-time deterministic performance. Because you're sharing resources like memory and CPUs and I/O, how do you know that a piece of software that has to execute in a microsecond is going to be able to access in a microsecond? And this is an area where the where the aerospace industry has really led. There's a whole lot of standards, CAS 32A and a number of other cert things, and we're seeing this increasingly become a focus for robotics, flying taxis, other autonomous vehicles. So you're going to see a lot more of this type of terminology, worst case execution times, things like micro benchmarking. You'll see that coming more into industrial markets as well over time. So let's just have a quick look at a couple of systems let me build out this slide. So how would this work out? You basically have to have a hypervisor because you're compartmentalizing the different software pieces, and you're really trying to isolate those individual pieces. So no sharing of memory between applications, no sharing of memory between the application and the hypervisor. You're basically allocating hardware per virtual machine, and you start to then get to a place where you can know that your ADAS technology is going to be guaranteed CPU resources to apply the brakes in a guaranteed time. It's not perfect. I will not lie. On today's silicon, you still have contention between applications, but you certainly set up this system, and then a combination of analytics and experimentation and a few other techniques to separate out tasks, you can start to work towards a path where you have deterministic real-time performance on multi-core platforms that are sharing resources with other operations and applications. So you'd see this sort of split out where you have ADAS running in a virtual machine. You would have very controlled access, so only certain elements have access to the internet. You would have secure communication between applications, through FIFOs or Ethernet or whatever. But that would all be prescribed and would not be accessible for a general user writing applications. This would be down really for the system architect to define that, as opposed to anybody else having access. So, and what that could look like in robotics, and this is an area where I think we will see good growth in the coming months and years post-COVID. I think all sorts of robotics, whether it's in factories or hospitals, we're going to see a diverse set of, or warehouses actually, I think we're going to see a diverse set of robots. And what's going to change is that rather than robots being in a fixed box in a factory doing a fixed task, we will start to see more collaboration between humans and robots. I'm starting to see things in Detroit where there's a particular task on a car manufacturing line. They will split up the task between a person and a robot working far more collaboratively, rather than it just being the human finishes and then hands it off to the robot for the next stage. And again, really need to split up critical functions, safety functions, and basically isolate those functions, isolate the memory, isolate resources wherever possible, and so that something in a general Linux application cannot access and mess around with the memory area that that safe operating system is using for its own application. So I think at a very high level, you're going to see that type of architecture roll out in robotics, a number of other areas, and it's really going to come down to those key fundamental pieces of crypto security, which I mentioned in hardware, but you also have to think about from a software perspective. Isolation, determining performance that you absolutely have to have for your real-time areas, and making sure as much as possible that other things going on that multi-core platform cannot interfere with that particular task. Thanks very much for your attention. Hopefully you found that useful.